Welcome to the lecture module on optics. We are discussing wave optics, and in particular we are now discussing the phenomena of diffraction. In the last lecture I have illustrated through various diagrams the phenomena of diffraction, and we have seen diffraction by a single slit, that is single slit diffraction. We have studied single slit diffraction. Today we will discuss the results of single slit diffraction and also go over to circular diffraction by a circular aperture. So, diffraction patterns due to a single slit and a circular aperture. So, first let us discuss the results, let us recall the results of single slit diffraction which we had studied in the last class, we have discussed in the last class. So, a parallel beam of light which is incident on a slit here. So, we have shown in 2D. So, a slit here, the light gets diffracted here and there is a corresponding intensity distribution on a screen placed at a distance L. When the distance L is sufficiently large, then we call it as Fraunhofer diffraction. The intensity pattern we have seen in the last class, the intensity pattern I of theta is given by I 0 sin square beta by beta square, and it varies like this. So, we have discussed this in the last class with minimas at lambda by a, 2 lambda by a, and on the other side of the central maxima minus lambda by a, minus 2 lambda by a, and so on. So, this axis is theta, sin theta, or which is very closely equal to theta. So, the intensity minima are given by beta is equal to m pi, because intensity minima are given by zeros of the sin square beta function here, except when m is equal to 0, except when m is equal to 0. We have seen in the last class that when m is equal to 0, which corresponds to this point, we have sin x by x or sin beta by beta is equal to 1, and therefore, except m equal to 0, the minimas are given by zeros of the numerator, namely zeros of the sin square beta function. So, that is when beta is equal to m pi, m is equal to plus minus 1, plus minus 2, and so on, which means sin theta minimum are given by m times lambda by a, where a is the slit width, m is equal to plus minus 1, plus minus 2, and so on. That is, m on this side is minus, m on the other side is plus. Now, as we know that a is typically, the aperture size is typically of the order of 0.1 millimeter here, and lambda by a we have seen in the last class with some typical numbers that lambda by a is much less than 1, which implies sin theta can be approximated to theta, or the minimum theta minimum is given by m times lambda by d, lambda by a. That is why we have written here m is equal to 1, m is equal to minus 1, m is equal to minus 2, m is equal to 1, m is equal to 2. So, the minima of the intensity minima of the diffraction pattern are given by theta min is equal to m times lambda by a, m is equal to plus minus 1, plus minus 2, and so on. What about the maxima? This maxima, of course, we have already seen is I 0, but what about these maxima and where do they occur? In the case of interference, we know, in the case of interference fringes, we know that the maxima occurs exactly in between the minimas, whereas in this case the maxima does not occur exactly in between the two minimas, and therefore, how to find out the intensity positions of intensity maxima. So, let us see this. So, for that we have to differentiate, the function. So, here it is. So, we go here. So, let us look at this. To determine the intensity maxima, we have d I by d beta should be equal to 0. We put this equal to 0, which means d by d beta of this is equal to 0. You simplify this. So, that is 1 by beta square into 2 sin beta cos beta minus 2 beta into sin square beta equal to 0. So, 2 is common, 1 by beta square is common, 1 sin beta is common. So, what you will be left is tan beta is equal to beta. The intensity maxima correspond to this equation, tan beta is equal to beta. This is a transcendental equation. It cannot be solved analytically, it can be solved either numerically or it can be solved by graphical solutions. So, what I have shown here is the graphical solution. Look at this. So, what is plotted along this axis is beta. There are two functions which have been plotted, the tan beta and beta. So, the blue ones are tan beta, this is tan variation, as you know that tan theta is 0 here and tan theta goes to infinity at pi by 2 and again starts from minus infinity, goes to 0 and goes to infinity. So, this is the tan theta function, tan beta versus this axis is beta, and this is y is equal to x, that is y is beta and x is also beta, y is equal to x. So, left side is beta, y is equal to beta, and the left side here is tan beta, the blue colored function, and right side here is beta. So, the intersection of these two, which means when they have both the same value, that corresponds to the point of intersection. For example, here there is a point of intersection, there is a point of intersection here, there is a point of intersection here. So, these give us the solutions corresponding to the maxima. So, the first maxima, the 0 is of course the maxima, we know that. We are looking at the occurrence, the maxima, the first maxima on each side of the central maxima. So, this maxima occurs at 1.43 pi and the second maxima occurs at 2.46 pi. So, what are we looking at? We are looking at this diagram here, this diffraction. So, this diagram here. So, what is the position of these maxima, this maxima and this maxima? This we know occurs at 0, theta is equal to 0, sin theta equal to 0 or theta is equal to 0, the central maxima. We are looking for the position of the maxima, secondary maxima which are here on the sides. So, these occur at 1.43 pi when theta is equal to 1.43 pi, and one more maxima which would come later would occur at theta is equal to 2.46 pi. So, that is the positions of maxima. So, we can see here the solutions are given by beta is equal to 0, beta 1 is equal to 1.43 pi, beta 2 is equal to 2.46 pi and so on. Why this is important? Therefore, the intensity of the first maxima is equal to, substitute I1 is the intensity of the first maxima, intensity of the first maxima, I1 is this value, this is I0, this value here corresponds to I1, intensity of the first maxima. We want to see how much this is relative to this maxima I0. So, intensity of the first maxima is given by I1 is equal to I0 into sin square 1.43 pi, because this is the solution beta value where the maxima occurs, divided by beta square. So, this is sin square beta divided by beta square, which comes out to be 0.0496 times I0, that is less than 5% of I0. So, this value here, that is if I show here, this value here is less than 5% of the maxima, central maxima, which means we have a bright central maxima and the maxima on either side of the central maxima are relatively weak. They are brighter, but they are relatively weak compared to the central maxima. Similarly, if you put the second maxima, then we will get I0 into sin square of 2.46 pi, the second solution, and divided by 2.46 pi whole square gives us 0.0168 I0, that is less than 2%, 1.68% is the intensity. So, the maximas are the secondary maxima on both the sides are much smaller in intensity compared to the central maxima, unlike the case of interference fringes. Now, let us go further. So, this is about the maxima, and therefore, we also recall now the single slit diffraction experiment. So, let us recall the single slit diffraction experiment. So, let us look at the experiment. This is the experiment which we saw in the last class. So, there is a laser beam which is incident on a slit. Here is the slit, and it gets diffracted onto a screen which is at a large distance. Typical numbers I have given. The diameter of the laser beam is about 1 to 2 millimeter, but I have shown it as a thick beam because the diameter of the aperture here, the slit width is of the order of 0.1 or 0.2 millimeter. Therefore, compared to the slit width, the laser beam is relatively thick. That is why I have shown a thick laser beam which is incident here of the order with dimension of the order of 2 millimeter, and getting diffracted at this slit, which is a adjustable slit. We have seen in the last class that by varying the slit width, we can change the diffraction pattern seen on the screen. So, the diffraction pattern seen on the screen is given by this. So, diffraction pattern on the screen. Now, we see that these minimas correspond to lambda by A in angle in theta. The angle theta is also given by. So, if this, for example, this corresponds to first minima, then this is theta 1. If this is theta 1, then theta 1 is given by, if so, this is 2 L, this is the linear width here 2 L, then the L, so 2 L is here. This is capital L is the distance to the screen, which is much larger, it is 1 meter, about 100 centimeters, and therefore, 2 L can be written as L into 2 theta 1, twice theta 1, that is, this is theta 1 which is lambda by A minus lambda by A on the other side, and therefore, the net total angular separation here is 2 lambda by A, and therefore, L into 2 lambda by A, L into 2 lambda by A will give us this 2 L, the linear separation 2 L. So, that is how we have written 2 L by L is equal to 2 lambda by A, or lambda is equal to L into A by capital L. Now, this I have shown because by measuring to determine the wavelength of light, one can measure the separation 2 L. In an experiment, we can measure the separation 2 L using a graph paper for the screen. For example, you paste a graph paper on as the screen, then you can find out what is the separation here, and measure A, the slit width, using a travelling microscope. Using a microscope, we can determine the slit width A, and L can be measured because it is a long length. L can be measured easily using a scale to determine the wavelength of the laser. Please see that the wavelength is much less than 1 micrometer, that can be determined by making practical measurements of this 2 L, the width of the slit under a microscope, and then L here using a scale. And this is a standard experiment now in most undergraduate courses. So, you to determine the wavelength of light using single slit diffraction experiment. Okay. So, let us go further. Let us now come to the double slit experiment. Let us relook at the double slit experiment. This is the double slit experiment where we have a parallel beam of light. Parallel beam I have taken so that we have one wave front reaching the two sources here S1 and S2, the two holes or two slits S1 and S2. So, that one wave front reaches. It need not be plane wave, it can be a spherical wave also, but one wave front has to reach the point here, because the point here S1 and S2 are considered in phase. And at any arbitrary point P, the intensity is given by I is equal to 4 times I 0 cos square delta by 2, where delta is equal to k times R 2 minus R 1 is the phase difference. R 2 minus R 1, R 2 minus R 1 is the actual optical path difference, and k multiplied by the phase constant gives us the phase difference delta. K is equal to 2 pi by lambda. We can see here that if the sources are separated by a distance d, separation d, then this angle here is theta, then the path difference, this is the extra path difference. We can see here this is the extra path difference. Up to this is R 1 and this is also R 1, but this extra thing makes it R 2 larger than R 1. This extra path difference R 2 minus R 1 is can be written as d times sin theta, d and sin theta. This is theta, therefore, this angle is also theta, and therefore, this extra distance is d times sin theta. Therefore, delta is equal to 2 pi by lambda into d sin theta for large values of d. Now, why I have written this, it will be clear that therefore, delta by 2 is equal to pi by lambda into d sin theta. Delta by 2 is equal to pi by lambda d sin theta. Now, taking into account when we did this calculations, we did not consider the finite width of the apertures. We considered these as 2 point sources which are in phase. S1 and S2 were 2 point sources which are coherent. That is how we started to get this expression. Now, we know that whenever the slits here always have a finite width, every practical slit will have a finite width A, and we know that whenever there is a finite width of the slit, then there will be diffraction effects which come into play. So, light coming through this aperture will diffract, light coming through this aperture will also diffract, and therefore, the interference pattern, the intensity distribution on the screen will be affected by diffraction at the 2 sources, 2 holes here or 2 slits S1 and S2. Taking into account the finite size of the slits S1 and S2, the intensity distribution on the screen is given by an expression of this type: I of theta is equal to I 0 sin square beta by beta square into cos square gamma. The derivation of this expression is beyond the scope of the discussions that we have here, but the results are important for us, and therefore, we will discuss the results here. So, I of theta is equal to I 0 into sin square beta by beta square into cos square gamma. Note that this first term here is nothing but the diffraction term, which we have just seen that this is the intensity distribution in the diffraction pattern due to an aperture of size A, due to a slit of size A. This cos square gamma, gamma here is pi by lambda into d sin theta, which is the same as this delta by 2 pi by lambda into d sin theta. So, the cos square delta by 2 here is nothing but the cos square gamma. So, now we have the intensity distribution, which is a function, it is a product of 2 functions I 0 sin square beta by beta square and cos square gamma. How would this look like? We can look at this. How would this product look like? So, we know the first one. So, I want to see what will be the net effect. So, I is equal to I 0 into sin square beta by beta square into cos square gamma, cos square gamma. So, gamma is equal to pi by lambda into d sin theta, delta beta is equal to pi by lambda into a sin theta, Remember that A is much smaller than D. D is the separation between the 2 slits and A is the width of the slits. typical number, just for our consumption, that typical number of A is 0.1 to 0.2 millimeter here, and typical number for D is of the order of 1 millimeter. So, you can clearly see that A is much smaller compared to D, and therefore, if we plot this graph, the first part here. So, let me plot the first graph. So, we have already plotted this graph diffraction. So, let me use a different color here. So, intensity maximas and minima. So, this occurs at lambda by A, and it is a symmetric function. So, symmetrically on the other side we have minus lambda by A, the first function, and this is 0. The second function, so let us plot the second function here. How would this look like? This is cos square gamma. Cos square gamma varies between 0 and 1. So, this is the level, and it varies between cos square. So, this is 0 and 1. It is symmetric. My graph may not be symmetric, but it is a symmetric variation on both the sides. This is 0, and the maximas. So, we know that when the maximas occur, when gamma is equal to m pi, cos square gamma, therefore, gamma is equal to m pi gives us the maximas, which means the maximas occur at lambda by d. So, this is at lambda by d, this is 0 lambda by d. The second maxima occurs at twice lambda by d, third occurs at 3 times lambda by d, and so on. Now, why did I show this much rapid compared to this? Because d is much larger than A. Therefore, this is a bigger number compared to this number, and therefore, the cos square gamma, gamma is a bigger number, which means the cos square will vary rapidly compared to sin square beta. If beta and gamma were identical, then they will vary identically at with the same period, but because gamma is much larger, this varies much rapidly here. So, lambda by A may be somewhere here. So, lambda by on the same scale, I am showing on the same scale. So, this point is lambda by A here, because A is smaller, and therefore, lambda by A is a larger number compared to lambda by D. So, what we have seen is this is nothing but the interference fringes. So, interference fringes, sin square cos square fringes, and this is the diffraction pattern due to a single slit diffraction pattern. And what is the net result? Net result is product of this into product of this. So, product of the two functions. So, when we take product of the two functions, wherever any one of the function is 0, the product is 0, and therefore, the net result will be. So, let me draw the net result now here in the next sheet. So, I have drawn by a dotted line, because the diffraction pattern acts like a envelope to the intensity variation here, and the net variation will be like this. So, intensity varying, becoming maximum, reducing, maximum, reducing. The amplitude is reducing because the diffraction amplitude is reducing. So, this is the, so here intensity is 0, and then again we have intensity variation. Same thing on the left hand side. So, this is the net intensity variation which looks like fringe pattern, but it is with the amplitude of the fringes, unlike in the case of interference fringes, these were all of constant amplitude. Now, the amplitude goes on dropping down. So, what I have plotted is intensity here versus the angle theta or sin theta. So, I is equal to this. So, this is I 0. This is the interference pattern. Now, what is important is the following. So, before I go proceed further, let me put a pre-drawn diagram here, and let me give put a nicely drawn diagram to give a better feeling here of. So, here it is. So, this is. So, what I have shown is the double slit diffraction pattern. It is our double slit interference pattern. You can call it as diffraction pattern or interference pattern. Interference pattern and diffraction pattern both are obtained by superposition of waves, superposing the waves at any given point. That is how we get the intensity due to diffraction or due to interference. And therefore, here I call it as double slit diffraction because we have taken into account the diffraction effect. I have plotted this very carefully for a particular separation d is equal to 4 times A. That is, the separation between the two slits in the Young's double slit experiment is d, which is 4 times the aperture size, slit width. And then we get, as you can see, whenever it is half times lambda by d, look at the blue curve, this is the interference fringes. Whenever it is at half times lambda by d, 3 by 2 times, 5 by 2 times, there are intensity minimas, that is m plus half pi by 2, m plus half pi. And whenever it is m pi, we have maximas. These correspond to m pi. Therefore, lambda by d, twice lambda by d, 3 times lambda by d, we have the maximas which are here. And the envelope here shows the diffraction pattern, the intensity variation due to diffraction pattern, which actually modulates or which affects the maximum intensity of these secondary maxima. The interference fringes are called the secondary maxima within the within the central fringe due to the diffraction pattern. Now, look at this point here. By chance, for this particular case, this happens to be 4 times lambda by d. As far as interference is concerned, we expected a maxima. This should have gone up here to a maxima, but when lambda 4 times this point is, when theta is 4 times lambda by d, this is lambda divided by d by 4, d by 4 is A, that is it is also equal to lambda by A, and we know that the diffraction pattern is 0 here. The diffraction goes through the minima at lambda by A. Therefore, for the case of d is equal to 4 times A, we have the 4th order maxima missing because it coincides with the 0 of the diffraction. So, that is why I have written here that it is also called the missing 4th order. There is a missing order because the diffraction 0 of the diffraction pattern eliminates or makes the intensity at here 0, because it is a product of the two functions. Now, if d were 4.5 times A, then the 5th minima here 4.5 times A is 9 by 2 times lambda by d is a minima here, interference minima. Interference minima and the diffraction minima would have coincided here. If d were 4.5 times A, both the interference minima and diffraction minima would have coincided here, and we would have got an intensity maxima here and then minima. There would not have been any missing secondary maxima. It is quite simple, and we can try to understand this very easily by looking at the product of the two functions. An important point here is, if A is much smaller than D, then this point will start moving away, and as it moves away, the diffraction minima would go far away, and we have many more fringes within the first diffraction maxima, within the central diffraction maxima, and the case would look like this. The case would, if A is much smaller than D, then there will be a large number of secondary maxima between sin theta is equal to plus minus lambda by A, that is the first zeros of diffraction. And then the interference pattern would look like this. It is slowly going towards 0, but before it reaches 0, there are many fringes which are nearly equal intensity, they almost look like of the same intensity, the double slit interference fringe. So, this, if we look only at this portion, it looks as if we are looking at the Young's double slit interference experiment. There is a small variation in the amplitude of the bright fringes as we move towards the periphery. As we can see, this is what I had shown earlier, that a computer generated interference pattern, double slit, Young's double slit interference pattern. You can see that the brightness of the fringes decrease as we go to the periphery, brightness of the fringes decrease, and this is because of the diffraction effects. The diffraction effects, taking into account the finite width of the aperture, finite width of the, so it is the same as you can see here. So, the intensity goes on decreasing from the central maxima, intensity goes on decreasing as you go to the periphery. Now, we come back to the basic idea of Fraunhofer diffraction, where if you want to perform a Fraunhofer diffraction in the experiment in a laboratory, you cannot have large distances to the screen, and then as we already said that we use a convex lens and place the screen on the focal plane of the convex lens. So, let us see therefore, how would the fringe pattern look like. So, we want to see now. So, I have now come to a laboratory setup where we have a parallel beam of light incident on the slit of size A, and a lens here, a convex lens, helps us in collecting parallel beams at different points P here. Therefore, the intensity distribution here for different theta will correspond to an intensity distribution here with the different x coordinate here, different x positions x. So, if the point P on the screen here, so you can see that this corresponds to intensity minimas. So, there will be a diffraction pattern on the screen which is on the focal plane of this lens, which would look like this, the intensity pattern. And what I have shown is, if we flip, this is a 2D, but if we flip the screen, so we can see that there will be intensity maximas and intensity minimas. The dots here, I have used dots to show that the high dot density means intensity is high, and low dot density means intensity is low, and no dot means it is a intensity minima here, because it is a continuous variation. So, we cannot exactly say that bright and dark, bright and dark, but it is a continuous intensity variation. So, the dot density corresponds to the magnitude of the intensity here. So, if the point P corresponds to an intensity minima here corresponding to this, so we are looking at this width here, the width of the central bright fringe, then corresponds to the first intensity minima, then sin theta is equal to lambda by A. And since lambda by A is much less than 1, we have discussed this several times, lambda by A is much less than 1, sin theta is nearly equal to tan theta equal to theta. An approximation is a very good approximation here, is equal to lambda by A. Now, tan theta here is W, that is the position of this point, the distance of this point with respect to the central maxima here, center W, then W divided by F gives you tan theta. tan theta is equal to W by f. Therefore, we have equated W by f is equal to lambda by A. W by f is equal to lambda by A. What is W? W is the linear width on the screen. Please see, till now we have been seeing the intensity distribution as a function of theta, that is as an angular distribution, but now we are seeing a linear distribution of the intensity along x here, and therefore, we want to find out what is the separation, linear separation, not angular separation, linear separation between these two, which is 2W in the figure. So, we have therefore, the linear width of the central fringe on the screen here is 2W is equal to 2 times f into lambda by A. Please see here, W is equal to f into lambda by A. Therefore, 2W, that is the width of this central maxima here, is 2 times f into lambda by A. Now, before I proceed to the circular aperture, I want to take a couple of examples to make us familiar with the numbers involved. As I have already told you, the application of a single slit diffraction experiment, where we can determine the wavelength of light if we perform the diffraction experiment and measure the separation between the first two minima. So, here is an example. In a single slit diffraction experiment, a parallel beam of laser light is incident normally on a long narrow slit of width 0.1 millimeter. The diffraction pattern is observed on a screen placed at a distance of 1 meter on the other side of the slit. If the separation between the first intensity minima on either side of the central maximum is 13 millimeters as observed on the screen, determine the wavelength of the laser. So, this is an example which illustrates the application of single slit diffraction. So, let us work this out, let us understand the problem. So, there is a slit here. So, a slit whose width is given, the slit width is given. So, slit width given that A is equal to 0.1 millimeter, A is equal to 0. There is a parallel laser beam which is incident here and which undergoes diffraction, and we see the intensity distribution on a screen placed at a distance L is equal to 1 meter, is 100 centimeter, L is equal to 1 meter. What is given is, we know that on this screen due to single slit we get a diffraction pattern like this. So, here, and in terms of angles this corresponds to lambda by A and minus lambda by A, here minus lambda by. This is L, and therefore, we are asked to determine what is the wavelength of light, determine the wavelength of light. So, what do we know? The minima here, what is the theta? So, the angle theta from here to here. So, this is given theta. So, theta is equal to lambda by A. Here. We are given this separation here, this separation 2W is given. So, we are given 2W, the separation 2L or 2W is equal to 13 millimeters. So, please see the question again. A long narrow slit of width 0.1 mm. The diffraction pattern is observed on a screen placed at a distance 1 meter, L is equal to 1 meter. If the separation between the first intensity minima on either side of the central maximum is 13 mm as observed on the screen, which means linear, this is 13 mm. If it was angular separation, it would not have been 13 mm, it would have been some degree or some arc of a second or something like that. It will not be in millimeter. The fact that it is given as 13 mm tells us that it refers to the linear separation here from here to here. Therefore, this angle theta we know. So, this theta, so tan theta is equal to, therefore, tan theta is equal to this half we know. So, this is L and L, this is given is equal to L by capital L, L by L, which is equal to 13 by 2, that is 6.5, half of this separation divided by 1 meter. So, this is millimeter, 13 by 2 millimeters. So, 10 power minus 3 meters, and this is 1 meter here. So, this is tan theta, and theta is equal to lambda by A. So, this is also equal to lambda divided by A. A is 0.1 millimeter, 0.1 into 10 power minus 3 millimeter, and therefore, lambda is equal to, so let us find out, therefore, lambda is equal to 0.1 into 10 power minus 3 here into 6.5. So, this is 13 by 2, 6.5 into 10 power minus 3 millimeter. So, that is meters now, all are in meter, divided by, in the denominator we have 1 meter. So, all are in meter. So, this much. So, therefore, we get so many meters. So, that is 6.5 into 0.1 is 0.65. So, we have 0.65 into 10 power minus 6 meters, 0.5 into 10 power minus 6 meters. So, let me write here itself. So, this means it is 6.65 micrometers. So, that is equal to 0.65 micrometer or equal to 650 nanometers. So, 650 nanometers. This corresponds to, what is this color? This is red color. So, this corresponds to, this is actually a typical wavelength of visible red color diode lasers which are used in laboratory. So, 650 nanometer is a red colored diode laser. So, we have got the wavelength of light as 650 nanometers. So, this is clearly, this is an experiment which can be performed in the lab to determine such small numbers as wavelength of light. Okay. So, let us take one more example. Let us take a second example. In a single slit Fraunhofer diffraction experiment using sodium lamp, wavelength is given, lambda is 589 nanometer. The separation between the two first minima on either side of the central maximum is found to be 5 mm, found to be means it is measured to be 5 millimeter. If the observation screen was placed on the focal plane of a convex lens of focal length 15 centimeter, determine the slit width, slit width is A. So, we are given, so this now corresponds to the discussion that we had. So, here is the on the focal plane. So, let me recall this diagram which we have shown. So, we have a source and a screen is placed on the focal plane. Screen is, so what is said is the difference between the two first minima on either side of the central maxima is found to be 5 millimeter. This separation 2W is 5 millimeter. If the observation screen was placed on the focal plane of a convex lens of focal length 15 centimeter, which means f is 15 centimeters. We are given f, we are given 2W, we are given wavelength, and you are asked to determine the slit width A. Slit width is A. So, A has to be found out. So, we already have. So, let me, instead of deriving this again, use this formula here, right here, which is given. So, we have 2W is equal to 2 times f into lambda by A, or A is equal to we have to determine A. So, A is equal to 2 times F, F is given 15 centimeter. So, 15 centimeter. So, let me write in centimeter right now, into lambda divided by A divided by 2W, 2W would come here, that is 5 millimeter. So, 2W is given as 5 millimeter, this is given, F is given as 15 centimeter, and therefore, A is equal to, you better use all same units, therefore, 2 times A is equal to 2 times 15 centimeter. So, 15 into 10 power minus 2 meters into lambda, lambda is given 589 nanometers, that is 10 power minus 9 meters divided by 5 millimeter, 5. So, this is 2 W. So, 5 into 10 power minus 2. So, millimeter minus 3 millimeters. So, we can simplify this, as you see that this is 5 goes 3 times here, and 3 into 2 is 6, and this leaves 1 10 power minus 10 in the denominator, here minus 1 in the denominator, and here we have 10 power minus 9. Therefore, 1 minus 1 cancels with 1 minus 1 here, leaving minus 8 behind. So, 6 into 589 into 10 to the power of minus 8 meters. We can simplify this, you can multiply by 6. So, 6 into 9 is 54. So, 6 into 8 is 48 plus 5 53, 6 into 5 is 30. So, 35. So, 35 into 10 to the power of minus 8 meters, or 35.34 into 10 to the power of minus 6 meters. So, this is micrometers. So, the answer depending on the requirement you may have to write. So, this is micrometers. You can also write this in millimeter, which is equal to 0.03534 millimeters. You have to be familiar with all the units. So, any one of in terms of meters, here this is in terms of meters, and this is micrometers, and this is millimeters. So, you note that the slit width typically, I was mentioning that this is approximately 0.1 millimeter typically. So, this is a little less than that. So, this is 0.035 millimeter or so. So, we have taken these are two simple examples which we have taken. The objective being to become familiar with the kind of numbers which are involved, and the fact that diffraction experiment can be used to determine unknown quantities such as wavelength of light or the slit width if you know the wavelength of light. Now, we proceed further, and now we take the diffraction due to a circular aperture, diffraction due to a circular aperture. So, again I am illustrating first what is diffraction due to a circular aperture. Recall that diffraction due to a single slit. In a single slit diffraction, we had a slit of certain width, and when parallel beam of light is incident, because of as the width of the slit decreases, light will diffract in this direction to give you intensity maximas and minimas. That is, we had a parallel beam, and then I had introduced, recall how I have introduced diffraction. I introduced two wedges cutting the beam till they come to a narrow slit. Now, we are looking at a circular aperture. There is a parallel beam of light coming. If you have a circular aperture, the beam passing through the aperture will fully pass through when the aperture is fully open, but as you close the aperture, as you reduce the dimension of the aperture, it will start cutting the beam, that is, it will start blocking portions of the beam. And then as the aperture becomes narrower and narrower, the light which is coming on the other side will move more and more into the geometric shadow, leading to the diffraction pattern. So, that is what is illustrated here. So, come to diffraction by a circular aperture. A parallel beam of light incident on a circular aperture here, diffraction takes place, and on the other side you see what is called as an airy pattern. An airy pattern where there is an intensity maxima and minima, then again secondary maxima, minima, and so on. If you take a longitudinal section, that is, if you see a section of this along this line, let us say along this plane, if you see the section, then it looks like this. It looks exactly like the single slit diffraction experiment. This is the slit, actually this 2a is the diameter of this circular aperture, 2a is the diameter, and here we have intensity distribution along this line, which is plotted here, I of theta as a function of v. There is the intensity distribution due to a circular aperture, where v is pi by lambda into 2a sin theta. Now, this airy pattern, so let us see what is this airy pattern. The diffraction, the detailed analysis is beyond the scope of our discussions here. However, it is important to know these results for us, that the airy pattern, that is the intensity distribution due to Fraunhofer diffraction by a circular aperture, is given by I is equal to I 0 into 2 times j 1 of v by v whole square, where v is given by this. And what is this j 1? j 1 of v is the Bessel function of the first order. As I mentioned, that Bessel function is a special function, and at this level we are not familiar with, you are not familiar with the Bessel functions, but we still need the result, and why I introduce this I will let you know in a minute. So, if you plot the intensity distribution, you get an intensity distribution like this. So, which has minimas at 3.832, v is equal to 3.832 and v is equal to 7.016 on both the sides here. This is also a symmetric function. So, we get here at minus 3.832 and minus 7.06. So, what I have shown here is the intensity distribution here. Here is the intensity maxima, it is 0 at 3.832 v, and here it is 7.016, and this intensity distribution is called the airy pattern. The corresponding intensity pattern here on the screen is shown here, that intensity is maximum at the center and goes on decreasing. The boundary which I have shown here, the boundary corresponds to these points here. In other words, within this region between the two zeros, this within the boundary between the two zeros, what we have is this region, and this is called the airy disk, which is here. Almost 84% of the energy in the diffraction pattern is contained in the airy disk, and therefore, the diameter of the airy disk can be considered as equivalent to the spot size of the diffraction pattern. That is why this point is very important. We will see applications where we have to consider this diameter of the airy disk in the subsequent classes. We will discuss the applications of the airy pattern and diffraction due to circular aperture in the next class.